Okay, so no, come on. So, switch your packet. Switch. Let's see what you did. You had time yesterday. Okay, well, all you gotta do is fix the ratio. That's all you have to do. Yeah. Okay, so because you had to include the dartboard, the 24 by 24, just for the X region, X had a radius of 4, so 16. If you have 16 pi over 576, the exact answer, you will get full credit. Yeah. So, so then if they gave the approximate answer, so if they, huh? Because you have to subtract the radius for the Y circle from, you gotta take the X out to have the blue region. Okay, so, all right, so on 2, they wrote 20 pi over 576, that's exact. I'll give you credit for that ratio. Or if they gave the decimal, or if they wanted to give the percent. So like if they wrote 8% or 9% on number 1, and then 11% on number 2, I would give you credit for that as well. You round it to the nearest percent. And then number 3 was 28 pi over 576. Okay? Technically, because it's 28 pi, if there was a 576 pi, the pi's would cancel out, and then you could reduce the ratio. So this is like 28 times pi over 576. So he'd put the decimal for the pi, the 20. Okay, then I'll give you credit for that. All right, they have to have the reduced ratio. Number 4 was 3/10, 5 was 7/10, 6 was 2/5, 7 1/10, 8 was 1, and 9 was 1/5. Okay. So we see a pattern.
I see.
Okay, what do you see, Rahel?
Goes plus 2 or like plus another 2 plus 2.
Yeah, you're looking at, yeah, there's a plus 2, but look at the faces of vertices compared to the edges. Look at the value of the faces of vertices compared to the edges.
It goes up, add about minus.
Yeah, add them up. If you add them up and subtract 2, that would give your edge. Do y'all see that? Okay, so basically this is what they're trying to get you to see is Euler's formula. And Euler was a Swiss mathematician that noticed this relationship when it came to three-dimensional shapes that were made up of polygons. Okay, and so this is the formula that you need to kind of use for three-dimensional shapes. Basically, f plus v, which is face plus the vertice, always equals the edges plus 2. Okay, f plus v always equals e plus 2. These are your edges. F is always your faces, v are your vertices, e are your edges. So as long as I have 2 of the parts, you should always be able to calculate the other missing part. Now, so with that being said, if I know that the number of edges of the polyhedron is 6 faces and 8 vertices, could you figure out the edges? Because we got the faces and the vertices, right? So we know f plus v equals e plus 2. I know this is 6 and 8. So what would e have to be? Yes. Are we okay on that? So you could figure out the edge. Now, this relationship also works with two-dimensional shapes. Okay? You can reduce it to f plus v equals e plus 1 when it's only a two-dimensional shape. All right, so they are going to give you some basic representations of our three-dimensional shapes or figures we're going to use in here, especially when we get to calculating volume and surface area. The biggest thing is to understand the difference between a prism and a pyramid, and when it's a polyhedra and when it's not. So what they've already highlighted the basis for you, so you can see how they're going to name the shape. For example, the basis is triangle here, so they're triangular prism. You need to understand that the faces of prism are all polygons, except for the 2 bases, and that are congruent and they are parallel to each other. Your faces are also normally, your lateral faces are also normally rectangles, but I will show you some examples of when that's not the case. Okay. Now, if I'm looking at the faces of a pyramid, they're all triangles, except for the one base. The one base could be a rectangle, it could be a pentagon, it could be a hexagon. But the remaining faces would be triangles. Now, this example, this first one is polyhedron. The cylinder is not, because the circle is not a polygon. This pyramid here, this example that they're showing you, do you see how it's leaning? Okay, whenever it's leaning, we call that oblique. Okay, this will be an oblique triangular pyramid. But whenever we calculate different measurements, we still have to use the height that is always going to be perpendicular to the base. Okay? Okay? It's just the height. The height's just going to be the perpendicular distance from the base to the vertex. Okay? So even though this one is slanted, I'm still going to look for that perpendicular distance coming straight down to that base. And that would be the height. Whenever it's leaning, it's called oblique. Okay, so what you're going to do today, and we're going to practice a little bit together, and it's going to get a little challenging, but we're going to practice to make sure you understand how a cross-section occurs.
So what's the definition of oblique?
Oblique is when a three-dimensional shape is leaning.
I know, but I remember there was some show on
Boondocks, the cartoon?
Yeah, that was that show.
Okay. All right. All right, we're going to look at cross-sections, okay? Basically, it's just the intersection of a solid and a plane You can think of it like a very thin slice. Like if you were going to cut the three-dimensional shape, what shape would you see at that slice? All right. Now they did the first one, which you were going to do a couple together. You're going to name the cross section, name the actual 3D shape, and then determine if it has faces, vertices, and edges, and how many. Okay. Basically, we're going to use Euler's rule. So on this first one, this little rectangle here, the orange piece, that's what they're using to make the cut. Okay, that's the plane that they're using to cut. And they're trying to give you some hints here. See how they kind of darken this little triangle inside of there? So they're saying if I cut it horizontally and I open it up at that cut, what shape would I see there? And it should be that triangle. Okay, so the cross section is a triangle. That's the name of, it's the shape that we're looking for. The name of it is not always going to end up being the same, but the name of this is also a triangle pyramid. Now, why do you think the cross section and the name is the same? Yeah, it's parallel to the base. This cross section is parallel to the base, and that's why there's a relationship there. There are going to be times when the cross section is not parallel to the base, and so you get a different shape. Okay? I'll show you.
Right there, right?
Yep. Okay. This one right here. See, this one's not parallel to the base, number 5. All right, so here they did the faces, there's 4, the vertices, there's 4, and they went ahead and did the edges of 6. We know that 8 minus 2 is 6, so that works. That's Euler's rule. So on here, if I'm looking at number 2, and I cut it, this horizontal cut, this cross-section, what shape would it be? Yeah, so write down circle. The cross-section's a circle. What is the name of this 3D-dimensional? Yeah, it's a cylinder. All right, so is a cylinder a polyhedra?
No.
No. So are we going to have faces, vertices, and edges? No. So we can't use Euler's rule. So we're done. That's all we can do here. 2 of the faces, but they're not polygons. Okay? You're right. They're circles. Okay? All right. What would this cross section be?
Circle?
It'd be a circle also. What would the name of this 3-dimensional? Yeah, cone. All right. Can we use Euler rule on this? No, because it's not a polyhedron. Okay? All right, let's look at 4. Now we got a vertical cross-section, but if I cut straight down, what would the cross-section look like?
Well, I mean hexagon.
Yeah, hexagon. All right, what's the name of this 3-dimensional shape?
A hexagonal prism?
Yep, hexagonal prism.
Hey, I didn't even know that. Ooh, let's go.
All right, so how many faces does a hexagon prism have?
8 plus 2,
10 faces?
I mean,
Yeah, 6 plus 2, there we go. All right, how many vertices do we have?
12.
Yep. Hold up, I'm sorry. Yeah, 12, 6 and 6, right? Okay, 12. All right, how many edges should we have?
18.
Yeah, 18. Euler's rule, okay? All right, number 5, we have a vertical cross-section. We're cutting straight down the middle. What would I have if I open it straight down the hill? Yeah, this one is a triangle. Okay, the cross-section would be a triangle. What's the name of this 3-dimensional shape? Cone. All right, so could we use Euler's rule here? No, because it's not a polyhedron. All right, 6. What would the cross-section be? Yeah, it's a pentagon. Then the name of this 3-dimensional shape. Yeah, pentagonal pyramid. Yes. Okay. All right, so this is a polyhedron. So we have faces, we have vertices, we have edges. How many faces do we have? 6. Okay. Yes.
If the pentagon part of that base, if it was a square, would it be called a prism?
No, if the base was a square, it'd be a square pyramid. It's still a pyramid because the faces meet at one point at the vertex, and you have only one base.
Where would it be a triangular prism?
When you had 2 bases.
Oh, yeah.
Yeah. Okay. How many vertices do we have here? 6. Okay. Edges are 10. All right. 7. Cross section. Yeah, it's a rectangle. Okay. Can I say it's a square? What do I need to know for it to be a square? Yeah, if all the sides were congruent. All right, so What's the name of this 3D shape? Yeah, rectangular pyramid. All right, so faces, vertices, edges. Sorry, faces, 5. Okay. Vertices, 5 as well. Edges, 8. Okay. All right, now I'm cutting vertically straight down. On number 8, what would the cross section be? Yeah, it's a rectangle. Now, what's the name of this three-dimensional shape?
Pentagonal.
The base is a pentagon, so it's a pentagonal prism. No, we don't name the shape by the cross section. We name the shape by its base, the shape of the base. All right, so it's a polyhedra, so we have some faces, some vertices, and some edges. How many? Yeah, 7 faces. How many vertices do we have? 10. Okay. So then how many edges will we have? 15. Okay. All right, last one that we're going to do together. Circle is the cross section. Cone. All right, so 10 through 15 right now. You're doing them. We're going to check them. Okay. We'll give about 5-7 minutes. Hexagonal prism. Faces. Faces, vertices, and edges. How many faces does it have? 8? Yeah, and 18. Okay. Okay, this is rectangular. It's a rectangular prism, and you should have 6, 8, 12. All right, so what I need you to look at real quick, and I need to open it up. Go to your homework packet. Go to your homework packet for me, please. I just passed it to you. Okay, your first homework is going to be page 3, all, and page 6 to 8. All. They're not that many. Yes, all. All of them. Okay? Page 3, all, and page 6 through 8, all. Now we're going to do or look at page 3. It's going to be a little challenging. It's going to require you to kind of think outside the box. Because we're going to do some in class, that's why.
Wait, can you say it again? I wasn't ready to,
Okay, page 3, all, and page 6 through 8, all. Okay. Huh? Thursday. All right, so let's look at page 3 together. We're going to start on this, okay? Basically, what they want you to do here is we're going to sketch a cross-section on the cube. Each time we look at it, it's a cube. That means all faces are congruent. They're all squared, okay? But when we sketch the cross section, when we show where we could cut it, they're telling you what they want the cross section to look like. So like on this first one, we want the cross section to be a square. So where would I have to cut the cube so I could see a square when I cut it? All right, so right. Okay, so I would right in the middle like this, like cutting it right down the middle. All right, so what you're going to do is you're going to draw it, and you're going to shade where that cross section would be. But you got to show that it's a square. Like whatever you draw, it has to match the shape of this cross section that they've asked to have. Okay? All right, so where could I cut so that my cross section was now a rectangle? So because if I cut this way, wouldn't I still have a square? Right? So that's not going to work. So we got to figure out a different way.
Wait, how do you know if it's a rectangle? Which way is
Huh.
the longer side?
No, there is no longer side. This is a cube. All the sides are congruent. Yeah, yeah, diagonal will work. If I cut here, and then there, and then there, there would make it a rectangle if I cut diagonal. Okay. All right, now we want to cut it so that we would have a trapezoid. Okay. 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 We want the trapezoid. So think about it. It's kind of similar to this rectangle. I want to cut it. So we want to basically, whatever we're drawing, wherever we're making our cut, we're basically drawing the cross section inside the cube because that's what we're going to see the way we cut it. So basically, we're going to have to go like here and then down to this side here, to that corner. And then this would have to go to this corner. And wouldn't that make a trapezoid?
I knew it.
Okay. There's my cross section.
Why is it so complicated?
Because I want to make you think a little bit. You got to work on your spatial reasoning. You're not having to cut, but you're going to have to visualize things differently, especially when we look at surface area and I start changing the orientation of the shape. Okay? We might be using those. Okay. All right, so, all right. Now, are you seeing that you're going to have to think outside the box a little bit? Because this, yeah, inside the box. All right, so think about it. I just gave you a regular trapezoid. What would you have to do to make it an isosceles trapezoid? Think about that.
You just go, you right instead of
You just put the markings on there? Yeah, that would make it true. But how would we know that for it to be isosceles, these have to be the same? So what would have to happen so that the legs are the same?
You gotta go like that.
You got to go where?
Wait, you gotta go like that. Can you do it from a base?
Yeah, can you make it down from the edges?
Can you make it from a base?
So you're cutting from which face? Like
Like a slit in the middle.
Isosceles trapezoid?
oh, like so you're coming from the middle of the face, but you got to go to another part, like because you're cutting through the cube. Try, and then we'll talk about it. I'll give you some time to try.